Welcome to this video, which is the introduction to exponential functions. This video is by Online Math Academy for all math tutoring and exam prep needs. Visit onlinemathacademy.com or visit me on Facebook at www.facebook.com/onlinemathacademy. Okay, so first, as we introduce exponential functions, we have to define what an exponential function is. And the exponential function f with a base a is denoted by the following. F of x equals a to the x. And you'll see that right here. So just a little recap. Before I say this, I should say that a is positive, but a is not equal to 1. And I'll tell you why that is in a second. And x is just any positive real number. Or, sorry, any real number. Not positive. It could be positive and negative. Or really 0, but 0 is not very exciting, and I'll also explain that later. Okay, so before we start talking about exponential functions, let's go back to talking about just this expression right here, a to the x. A to the x is called a power of a. The real number a there is called the base of the power. And the x is the exponent. So you have this power of a to the x, you have a base of a, and you have an exponent of x. So let me just clean it up here. Now that we have our terminology down, let's talk about what these expressions kind of look like if we plug in numbers for a and x. So I'm going to deal with the function. I'm going to define this function right here. F of x equals 2 to the x. And let's just play around with this a bit. So let's let x equal 3. So f of 3 is 2 to the third, which is 2 times 2 times 2, and that's 8. Let's look at what happens when we let x equal negative 3. So it's f of negative 3, and all we do, like we did above here, is wherever we saw an x in this function definition, we're going to put a negative 3. So it's going to be 2 to the negative third power. Now, what is 2 to the negative third power? And to answer that question, we have to recall something from before. So remember in exponents, if you have an a to the negative m, you can rewrite that as 1 over a to the m. So with that thought, you can take 2 to the negative third and rewrite it as 1 over 2 to the third. And we just saw above that 2 to the third was equal to 8, so 1 over 2 to the third is equal to 1 over 8. So notice that in this one right here where we let x equal 3 and we found f of 3 to be 8, notice we plugged in a positive number 3 and we got a positive output 8. Now also notice down here that when we had a negative input, negative 3, we got a positive output still, 1 over 8. Certainly 1 over 8 is greater than 0. So that's strange. We got a positive output for a positive input and a negative input. So what happens when we let x equal 0? And this is the very non-exciting thing. So if x is equal to 0, then f of x is f of 0. And f of 0 is 2 to the 0th power, right? Well, here's another thing regarding exponents that you'll have to recall to have this make sense. Any real number a raised to the 0th power is 1, and this is by convention. So in math, sometimes there are things that are just done by convention, and this is one of them. So whenever you see something raised to the 0th power, you can automatically say that equals 1. So really, anything raised to the 0th power is 1. That's why I said that it's not that exciting when x is 0. Because it's always the same thing, no matter what a is. It could be, we could have this function right here, g of x equals 196 raised to the x power, and g of 0 I can automatically say is 1 because g of 0 is equal to 196 to the 0th power, and by this right here we know that anything raised to the 0th power is just 1. Okay, so what did we see here? We saw for both positive and negative inputs and 0 inputs, we get positive numbers back. We got 8, 1/8, and 1. Okay, so that really tells us something about this function, and I'll go into this further, but really an exponential function, the function's value, this guy, and when I say this guy, I mean this guy, or this guy, or this guy, whatever we get back is always going to be positive. It's never going to be 0, and it's never going to be negative. And the reason for this is, and this is only if you have a positive base A. So A here is, again, positive. We're not working with negative A's. We are not working with negative A's. We are only working with positive ones. So if you have a positive, it all goes back to this. If you have a positive real number and it's raised to a negative exponent, then you rewrite it like this. And certainly this now, a positive number raised to a positive exponent, that's going to be positive, and certainly 1 is going to be positive, so a positive over a positive always gives you a positive. And of course, if you just had this and m was positive, then this is always going to be greater than 0 if m is positive. So as long as a is positive and m is positive, that's always going to be greater than 0. The point is, these function outputs are always going to be greater than 0. Always, 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 no matter if the exponent is positive or negative. Now, why not 1? Why not 1? Why don't we let the base be 1? How come we are not considering this right here? Let's say f of x equals 1 to the x. Well, the thing about exponential functions is, and you'll see this when we start going into their graphs, is they grow. They grow rapidly or they decay rapidly. So they either go like something like this or something like this. They either grow rapidly or decay rapidly. Well, what happens with this function right here? Let's try a couple different values of x. So let's let x be equal to -2, -1, 0, 1, and 2. And let's find out what f of x is for each of those values. So when x is 0, or when x is -2, you get f of -2 equals 1 to the -2, which we know by this guy right here, we can write as 1 over 1 to the 2. And 1 squared is just 1, so it's just 1 over 1, and you get 1. So f of x is 1 when x is -2. Well, what about if we made this guy a -1, right? What if we made this guy a -1? Then we'd have this, right? We'd have 1 to the -1 is 1 over 1 to the first power, and that's just 1 over 1, and that's 1. And the thing is, it's always going to be 1. F of x never changes. It's always 1. If the base is 1, f of x is always 1. So it doesn't grow or decay. The graph of that would look like this. It would just be this guy right here. And it would be passing through this point 0, 1 on the y-axis. And the x values, or the y values rather, would always be 1. The y values would always be 1. So the output never changes. It's always 1. So it's not really exponential. We call this a constant function, because it's constantly at 1. And so proceeding here, if we let x equal 0, in our equation in blue, or our function in blue, we get 1 to the 0, and we know by what I told you here that anything to the 0 is always 1. The next one, if x is equal to 1, 1 over 1, well that's 1, and if x is 2, it's 1 squared, which is also 1. So again, if the base is 1, it's a constant function. We don't really consider it an exponential function because it doesn't grow or decay like these guys do. It kind of just stays at 1 like we had over here. Okay, so let's get into what these graphs look like. Here, I'm going to deal with this top equation first. I am going to deal with this function f of x equals 3 to the x. Or, we can write it another way, y equals 3 to the x. Remember, f of x and y, you can always interchange them. Basically, what you're saying when you say f of x is equal to 3x is you said, okay, for some input x, what is the output f of x if we let x equal 0? And really, y equals 3 to the x is like, okay, y is the output, x is the input. So for every input x, you'll get a different, or not necessarily a different value of y, but for every input x, you'll get some value of y. So y corresponds to whatever x is. Y is the dependent variable or the output, and x is the independent variable or the input. So we're going to take a couple different values of x, and I've already kind of set up the graph so it's easy to do for us. Let's take these values. X is negative 2, x is negative 1, x is 0, x is 1, x is 2, and x is 3. And let's see what we get. I'm going to work down below here. When x is negative 2, f of x is f of negative 2, right? And what is f defined as? Well, up here it's defined as 3 to the x. So it's going to be 3 to the negative 2. And we know that we can write that as 1 over 3 to the 2. And that's going to be 1 over 9. So when x is negative 2, f of x is 1 over 9. How about when x is negative 1? Well, we're going to have f of negative 1 then, and that's going to be 3 to the negative first power, which we can rewrite as 1 over 3 to the first power, which is the same as 1 over 3. And that's what the output is. When the input's negative 1, the output is 1 over 3. Now, the next one's pretty easy, and you could probably recall it from what I told you on the last slide. So when x is 0, f of 0 is 3 to the 0. And we know that anything raised to the 0 power is what? Right, 1. So this is 1. When the input is 0, the output is 1. Let's finish up, and these are a little easier. So when x is 1, f of 1 is 3 to the first, which is 3. When x is 2, f is 3 squared, or sorry, I wrote that poorly. When x is 2, it's f of 2, and that's 3 squared, which is 3 times 3, 9. And when x is equal to 3, f is f of 3, and that's going to be 3 to the third, which is 3 times 3 is 9, times another 3 is 27. Okay? So let's fill these in. When x is 1, f of x or y is 3. When x is 2, f of x or y is 9. And when x is 2, f of x is 9. When x is 3, f of x is 27. So let's just plot these, and I'll show you how this function is growing exponentially. It's growing really fast. First it starts at these very low numbers, 1/9, 1/3, they're very close to 0. And then it gets a little bigger here at 1, and then it starts to get really large. It starts to go up by a multiple of 3, right? So this is times 3. and then 3 to 9 is times another 3. And that's exactly what we're doing in our function. And then this is times another 3. And we did times 3 from here to here too, of course. And let me plot that. So I gotta have up to 27 up here, so I'll just put 27, and then maybe this will be 9, and if that's 9, maybe this is 3, and maybe this is 1, and so at -2 we're at 1/9, so we're going to be very, very close to 0. We're not going to be at 0, but we're going to be very, very close to it. And then at -1 we're a little bit bigger. That's maybe even too big still. So we're going to get really, really close to the x-axis. And then we hit this point, 0, 1. And then our next point's right here, right? It's 1, 3, so that's going to be right here. And then our next point is 2, 9, and we're going to put that guy right there. And then our next point is x equals 3. And when x is 3, y, or f of x, is 27, so now we're going all the way up here. And I wrote the 4 there, but we never actually even got to 4, so I'll erase that. And what you see here is this function starts very close to 0. It doesn't ever hit 0 or go negative. And it goes along, and all of a sudden it starts shooting up exponentially. Now, maybe I will actually keep the -4 in there, and just to prove a point. So if this were not 4, or -4, sorry, +4, x is +4. If x was +4, f of x would equal f of 4, and that would be 3 is 9, times another 3 is 27, times another 3 is 81. So we would have to make our y-axis about 3 times larger than what I have here in order to be able to fit this on our graph. Obviously I didn't leave enough room for that, but I'm just showing you it starts to get very large very quickly. F of 5, so times another 3, is 243. So you can see this went from 1 to 243 really quickly. It was at x equals 0, it was 1. At x equals 5, it's 243. So it's like shooting up. When you say something's growing exponentially, what you're saying is it's becoming large very, very rapidly. And that's what's going on with something like this. Okay, so that was an example of a function with a positive exponent. A positive base, 3, and a positive, well, a positive variable exponent, so x, right? We took x to be, of course, -2 and -1, so then it turned to be a negative exponent, but as I wrote it, it was just x. Now let's deal with something that has a negative exponent in its function definition, so negative x. What's happening here at negative x? And, not what's happening here at negative x, sorry. What happens when the function is written like this? Well, let's find out. So again, let me write in my x values: -2, -1, 0, 1, 2, and 3. Alright? So let's see what happens when x equals 2, or -2, sorry. When x equals -2, f of -2, or f of x when x is -2, is equal to 3 to the negative, and then you just remember, you plug in this where x is, so x is up there, and you can go -2. Well, that's the same as 3 negative times negative is a positive, so it's 3 squared, and that's 9. And let's see what happens when x equals -1. So we have f of -1, and that's 3 to the -1, which is the same as 3 to the first, which is the same as 3. When x equals 0, we have f of 0, and that's 3 to the negative 0 power. Well, that's just the same as 3 to the 0, and that's anything raised to the 0 is 1. When x is 1, we have f of 1, and that's 3 to the negative 1, and that's the same as 1 over 3, and that's what you get, 1/3. When x is 2, we have f of 2, which is 3 to the negative 2, which we can rewrite as 1 over 3 squared. 3 squared is 9, so this is 1/9. If we let x equal 3, then f of 3 is 3 to the negative 3rd, which is the same as 1 over 3 to the 3rd, which is the same as 1 over 27. So when x is negative 2, f of x is 9 for this f of x. And when x is negative 1, f of x is 3. When x is 0, f of x is 1. When x is 1, f of x is 1/3. When x is 2, f of x is 1/9. And when x is 3, f of x is 1 over 27. So the highest value of f of x or y here will be 9. And then I'll put 3 right here. And I'll maybe put 1 right here. And let's plot these points then. So when x is negative 2, f of x or y is 9. So negative 2, we go up to 9. Plot that right there. When x is negative 1, f of x or y is 3. When x is 0, f of x or y is 1. When x is 1, it's 1/3. And 2 is 1/9, so a little lower, but still positive. And when it's 3, it's 1 over 27, so that's really, really, really close to the x-axis. And look what happens here. Kind of just trying to draw a curve here. And, it gets very, very close to the x-axis, but it'll never cross it. As x increases, it's going to be 3 to the negative larger number, right? 3, it's going to be 3 to the negative, and the number here, x, is going to get larger and larger and larger, right? So it's just we can always write this as 1 over 3 to the x. So basically, this will be getting, the x will be getting larger, so this whole thing, 3 times x, will be getting larger and larger and larger. And as this gets larger and larger, the denominator grows to infinity. This whole thing will be getting closer and closer and closer to 0. It will never be 0. Imagine having a pizza pie and having it cut into, I don't know, imagine if we did 3 to the negative 4th. That would be the same as 1 over 3 to the 4th, which is the same as 1 over 81. Imagine you had a pizza cut into 81 slices, right? But you still had one slice that was yours. You're always going to have your finger on one slice. So imagine if it got cut into 200 pieces, right? You'd still have your finger on one slice. As long as the 1 stays constant up here, which it is going to. It's not going anywhere. It doesn't change with x. You're always going to have at least 1 out of however many slices, whatever. So it'll never become 0 is basically what the point I'm trying to make. And this is called an exponential decay function. So you see that it decays really quickly. It loses output value. So the output value goes down. As x increases, the output decreases, and it gets closer and closer to 0 as the output increases, or the input increases. So as x grows to infinity, f of x goes to 0. Okay, so again, the green function was called a growth function. The red function is called a decay function. And growth and decay functions can be classified by their function definition. So if you have a positive x as in your function definition, that's a growth. If the base is positive, like it is here. And when the exponent is negative in your function definition with a positive base, you have a decay function. Okay, So let's talk about this growth function a little bit. So we're going to look at the general equation, or the general function rather, f of x is equal to a to the x, where a, and now we're going to say, okay, let's let a be greater than 1. And we're going to talk about this, if a is greater than 1, so the base is greater than 1. And so far, we have not talked about any kind of exponential functions where the base has not been greater than -1, or sorry, been greater than 1. So what's the domain of this function? The domain can basically be thought of as all the x values which you can plug in, which you get a defined value for. So a to the x is never undefined. It's defined everywhere. And since it's defined everywhere, the domain is -infinity to infinity. You can plug in any value or any real number here, like I said in the definition of the function, and it has a defined output value. We call this type of function a continuous function. Now, this is a little bit unimportant for your class, but it doesn't necessarily imply that a domain with a function with a domain of -infinity to +infinity is always continuous, but in this case it is continuous. Okay. So let's talk about the range a little bit. What is the range? The range are all the possible output values that the function can take on. And as we discussed, the output values, so the f of x values or the y values, and remember they're the same thing, they have to be positive, right? So the range has to be 0 to infinity. It can never, the y value or the f of x value can never be negative, and it can never be 0. And why? Because this guy, if you have this, it's going to be positive, and if you have this, it's going to be equal to this, and as we just said, this is greater than 0, and so up here you have something that's greater than 0 over something that's greater than 0, and that's going to be greater than 0. Okay, so that's why there. I think you probably understood that. The x-intercept, it doesn't have any. Why? Well, this goes back to what we just said right here. The y value never hits 0. So let's recall what an x-intercept is. The x-intercept is the value of x when y equals 0. Well, y is never 0. Ever. Ever, 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 ever 0. So there's no x-intercept. Of course. Okay, next, moving on. The y-intercept. Let's recall what the definition of y-intercept is. The y-intercept is the value of y when x equals 0. So let's just look at this function, and let's let x equal 0. So f of 0 equals some positive real number a that's greater than 1 to the 0th power. Well, what's that always going to be? No matter what a is, no matter if a is 3,000 or 3, it's always going to be 1. Any real number raised to the 0 power is 1. Always, always, always. So that's why when x equals 0, y equals 1. And the y-intercept for this type of function is 0, 1, excuse me. As I said before, this is an exponential growth function, and it grows very rapidly as x increases. And this is an increasing function then, and as x goes to infinity or increases, f of x also goes to infinity, so it also increases, and that's shown on the graph. What is the asymptote? The asymptote on this function is y equals 0, or in other words, the x-axis. The x-axis is y equals 0 because every point here on the x-axis has a y value of 0, and we write horizontal lines like this. Okay, why? What is an asymptote even, actually? An asymptote is an equation for a line that a certain function gets infinitely close to, but never crosses. And we've spoken in great detail why f of x will never be 0 or less than 0. It'll get infinitely close. So if we keep going more and more over here, this guy is going to get closer and closer to the x-axis, but it's never going to hit it. It can get infinitely close to it, but never hit it. As x goes to negative infinity here, f of x goes closer and closer to 0. Okay, let's finally deal with this guy, the exponential decay function. And remember, that's when in the definition of the function here, you have a negative in front of the exponent. Okay, so same setup as before. Now, what's the domain here? Well, just like the last one, it's negative infinity to infinity. Because you can plug in any x value and get a defined f of x or y value out of that function. What's the range? Well, same deal. The range is 0 to infinity, right? If I let x be negative 3, and I'm going to be dealing with f of negative 3 equals, and we don't even need to know a. Okay, a is greater than 1. Great. So a to the negative third. To the negative third. And that's going to be a to the third. And any positive number raised to the third power is certainly going to be greater than 0. What happens if x equals 30? A positive number. Well, it's going to be a to the negative 30. And we can rewrite that as 1 over a to the 30. And we know that this guy, a positive number a raised to the 30th power, is certainly going to be greater than 0. And obviously this is 1, so it's greater than 0. So it's a positive over a positive equals a positive. And so basically, no matter what your input is, negative or positive, your output will always be positive in a function that's written like that. I hope that's clear, and we really belabored that point here. Okay, segueing nicely into our next point, what's the x-intercept? So the x-intercept, again, is the value of x when y equals 0. Well, didn't we just say that y or f of x can never equal 0? Yes. So there's no x value when y equals 0 because y never equals 0. Moving on. The y-intercept. So it wants to know what's the value of what's the value of y when x equals 0. So f of 0 equals a to the negative 0, which is the same as a to the 0, and we know that is 1, all the time 1. Great. That's why this point's there. It's a decreasing function. It's a decay function, a decreasing function. So you'll see as the x values go closer and closer to infinity, as they increase, you'll notice that our f of x, our outputs, are getting closer and closer to 0. They'll never actually hit 0, but they'll get as infinitely close to 0 as you possibly can if you keep pushing x to the right, you keep increasing x, you keep making x larger. That's what a decreasing function does. And I didn't write this, but this function has an asymptote too, and it's the same line. It's the same line y equals 0. It's the x-axis, right? Because an asymptote is a line that a function gets infinitely close to but does not cross. And in this case, the function will get infinitely close to the x-axis, or the line y equals 0, but it'll never cross it. And we've explained why. I belabored that point. Because no matter what your input is, positive, negative, or 0, your output's always going to be positive. Okay. Now, it's important to know this last thing I wrote down here. That f of x equals a to the negative x is the reflection of f of x equals a to the x. Basically what's happening is, whenever you get an x value, so suppose this is some value x star, right here, right? Then for this guy right here, it's going to be f of x star equals a to the negative x star, right? Now, look what happens for this guy right here. And I probably shouldn't have named it f. I probably should have named it g, so I'm going to name it g now. So g of x star is a to the x star. And this is the same as 1 over x star, and this is just, sorry, 1 over a to the x star, and this is just what we have here. So we have this, and then we have this. So if we look at this point over here, x star, that's going to be negative x star, right? And it's going to be, basically, what I'm trying to show you, I'm not doing a very good job of this, but what I want to show is that the negative exponent one is the reflection across the x-axis of the positive exponent one. So this one that I drew in the pink is the one from over here, and the other one is one from over here. And they're like, you know, whatever I have over here, I have right here, and imagine they are equal. It's pretty clear. So basically, this guy and this guy are the same, except they're just reflected across the x-axis. Nothing else changes about them. But that's not incredibly important. So, what have we gone over today? We went over the definition of an exponential function. We took a look at this power expression after we kind of put down some terminology, and we saw that no matter what we plug in for x, that's always going to be positive. And if this guy a was 1, we showed that that's a constant function, something that always equals 1, not something like this or this, which is exponential growth and decay functions. Okay, we reviewed a little bit of our laws with exponents, then we actually graphed two exponential functions. This one was a growth function, and this one was an exponential decay function. And we went through how to not only find the outputs for the given inputs there, but we went and graphed them. And then we kind of talked about how rapidly they grow. They go up by a factor of 3 every time, or in the red case, it goes down by a factor of 3, or you divide it by 3 every time. So you go from 9 to 3, you divide by 3. From 3 to 1, you divide by 3, and you just keep dividing by 3. Think of the pizza pie analogy. Like if you have a pizza pie, and you divide it into 3 slices, 3 big slices. And then you're like, okay, I want to divide it some more. So you divide it into 3 times that slices. So you go 9 slices, and then you go 27 slices, blah, 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 blah. Basically, you're just always dividing it by 3. This is a growth function. We talked a little bit about what these things are like, what's the domain, what's the range, what's the x and y intercepts and y. We were told that this is an increasing function, and we talked a little bit about the asymptote. And then we did the same thing for decay, and we said that, okay, these two guys are reflections across the x-axis, or sorry, the y-axis. And, yeah. So this is the first part of exponential functions video. And there will be another video coming soon talking about the graphical transformations of these functions. So what happens when the function is changed a little bit, when it's not exactly this? What happens to our graph? What happens to our domain, our range, our intercepts? We'll talk about that. And then we'll also go into compound interest problems, and also this constant e. What is e? E is an exponential constant. It's kind of like pi, and we'll talk a little bit more about that. But I hope that you learned something, hope that you enjoyed the video, and I hope that it was very helpful. I am Michael from OnlineMathAcademy.com. Have a great, great day.